First of all, I would like to thank to the organizer of the 17th International Congress of Catalysis and to the North American Catalysis Society for all the work and effort they put to organize this Congress. We share their frustration because we cannot be together, all of us celebrating it. I am very honored, and it is a privilege to give today the Heinz Heinemann lecture. I knew Heinemann a long time ago, and I would like to tell you that Heinemann is in the origin of the catalysis in Spain. In the difficult years in Europe and also in Spain, he became a very close friend of Juan Francisco García de la Banda. García de la Banda was then making a small department on catalysis in one institute of physical chemistry. They became very good friends, and that friendship stayed for all the rest of their life. The first generation of PhDs that they were made in that department, Heinz Heinemann took care of them, take it as a postdoc into the United States, and put them to work in research centers from Howdery, Kellogg, Mobile Oil, and other universities. Among them was my mentor, Antonio Cortés. After the postdoc, they came back and they started, directed by García de la Banda, what became the Institute of Catalysis and Petroleoquímica in Madrid. And I am the third generation of those. So thanks, Heinemann, for your input into the catalysis in Spain. Today, in my talk, I will try to tell you about the main line and thoughts how we were thinking to develop the catalysts. Our model there were, in this case, were enzymes. In the enzymes, one of the characteristics of the enzymes is that they have well-defined single isolated sites. If all of them are the adequate for the reaction, if the site is the adequate for the reaction, then selectivity has to be very high. But enzymes, they are more than that. They have pockets in where the active site is present, and in where you have other groups that they interact with the transition state occurring inside of those pockets, and they minimize or decrease the activation energy for the process. So that gives to the enzymes the high activity and high selectivity. Well-defined single isolated sites, the presence of those pockets or cavities to enhance the rate and selectivity. If we try to translate that into solids, we have a limitation, many limitations, but one of them for sure is that solid inorganic catalysts, they are not as flexible as the enzyme they are. However, we thought that we could make it not only a bit more flexible, but we could better introduce the active site by engineering them if we prepare hybrid organic inorganic solids. So in this case, we can design what would be the active site by organic chemistry synthesis, then functionalize this one, condensate with silica, and make materials with large mesopores, large surface area, and having all the active sites that in this case we were locating them into the organic molecule accessible to our reactant. This type of materials could give us many possibilities. One would be to locate the site into the organic part. Another would be to locate it in the inorganic part, but also to have some in the organic and in the inorganic, and then to prepare multifunctional catalysts for cascade reactions, as you will see. So now, by organic chemistry, we are going to design the type of site when put it in the organic. Look, for instance, the reaction in where we are going to form a carbon-carbon bond. we have to activate here this hydrogen of this molecule. We have to abstract that proton, and for that we'll need a basic site. If it becomes more and more difficult to abstract that proton, then you will need a stronger and a stronger basic site. And that is not always the most adequate. Furthermore, in the case of enzymes, you don't have very strong basic sites. So it should be another way to go around. And another way would be to design a bifunctional type of catalyst in where we will have one basic site to polarize that carbon hydrogen and to generate a certain density of charge, and then one acid site to polarize the carbonyl here to increase the density of positive charge in the carbon, and then the nucleophilic attack will be much easier. So this is what we did, and make that molecule with two amino groups in where we protonate one of them. The idea will be to have together the basic and the acid, and to have them at the right distance in order to be able to make the transition state for the reaction that we want. So we prepare that, functionalize, make the hybrid organic-inorganic, and now we simulate what would be the reaction, and we saw that indeed when we separate them by one carbon, it was adequate to carry on the reaction, or at least to establish the transition state. When we make it, the reaction went very fast and the selectivity was practically 100%. To test the hypothesis, what we did then was to increase the distance between the basic and the acid site. That means to put 2 carbons, 3 carbons in between, and to see how that affected the transition state and the rate of the reaction. And we saw that already when you put 2 carbons, the activity of the catalyst decays, and when you put 3 carbons, the activity, the benefit, I would say, of the basic plus the acid site completely disappeared, and the remaining activity was just the one associated to the basic site. So we could design here now one hybrid catalyst in where we had the 2 functions we needed in the organic. But we can do it in another way. We can go now and to make one hybrid catalyst in where we locate one active site in the organic part, another in the inorganic part. We'll have the 2 sites, and therefore we'll be able to catalyze now consecutive reactions by the 2, in other words, to carry on a cascade one. So we took a 2D zeolite, ITQ-2, the first 2D zeolite that was ever prepared, and here we have the inorganic part. We have the micropores, zeolitic micropores, in where we can introduce here either acid or basic or metal sites. Then in between the layers, we take now one organic with this disilane, we anchor the 2 layers, and we pillar it with those ones, and we introduce basic sites in this one. We'll have galleries in where the molecules can diffuse, and they will have accessibility to the basic and to the acid site. So we have 2 sites. Let's make now one model reaction in where we want to react one acetal with malonitrile. So we need one acid site to hydrolyze the acetal, and then a basic site to carry on the condensation. So with this catalyst with the 2 sites, the reaction went very fast and very highly selective. This didn't happen if we had only one type of sites, either the acid or the basic. So 2 sites, same molecule, 2 sites separated. One thing was missing, and was how to introduce enantioselectivity. Well, to introduce chirality in a solid is not easy. It's not an easy task. However, we can introduce chirality in a hybrid catalyst because we can introduce it into the organic part. And that is what we did. We make now one hybrid in where in the organic we have the basic site that we needed, plus the chirality that we needed to carry on a 3D reaction in an enantioselective way. So this one, with the same hybrid silica material that I showed you before, but with the chiral basic sites, we could make the 3D reaction and to have very good conversion with very reasonable, acceptable enantioselectivities. So we had now many possibilities, active sites in the organic, in the inorganic, too close, chiral, so we can attack more complicated problems. Take, for instance, the synthesis of GABA products. GABA are pharmaceutical products that many of us we use, for instance, to sleep better. And here, in the industry, how this process is made is by using normally 4 or 5 steps. In each step, you have to separate the products, you have to purify it, you have to go into another one. One of the steps requires one chiral catalyst to introduce chirality into one of the carbons here. So now we have multi-purpose catalysts that we can prepare in where we could introduce the functions. We can go into another line of work, and we can carry on a 3D reaction with the catalyst that you saw before, with basic sites and chirality, obtain already the intermediate that you see here with the chiral bond, and now with a second function, which is a metal that we can have also, to hydrogenate and decarboxylate to obtain the final product. That means that we can do now the reaction in one pot, 2 steps, with a solid catalyst, with a hybrid catalyst. Well, in that case, the conversion that we obtained was higher than with the conventional, chirality about the same, and the amount of subproducts produced was much less. So you see how we are building now on hybrid catalyst, and then we look into another type of hybrid organic-inorganic catalyst. This would be metal-organic frameworks. In metal-organic frameworks, you can introduce active sites into the metal part. You can introduce also modifications or sites into the organic linkers that you have there. And for sure, in this tridimensional porous structure, you could also put nanoparticles in the pores, as our colleagues have done and have demonstrated. Long time ago, we saw also the possibility to put 2 types of sites and to carry on a cascade type of reactions. And this is one of them that we try, as I said already a long time ago, in the 90s. And here, we want to make these pharmaceutical products 3 steps. The first step is a non-catalytic step. Then we have the first catalytic one, which is a carbon-carbon bond formation through a Sonogashira reaction, and the second one, which is a click reaction to make the final product. You know very well that to catalyze the Sonogashira reaction, palladium is an adequate catalyst, as is even better if you have palladium and copper. And for the click reaction, copper is very adequate. So what can we do? We could take one of those MOFs and to introduce both functions close by. And then we had the opportunity to do the cascade reaction with that catalyst. So we took the copper BTC MOF, that it has in the nodes 2 coppers that they are saturated with water molecules, and we substitute 1 water molecule with a ligand where we attach a palladium, and we have now a catalyst with close by palladium and copper. And this was very selective for the reaction we wanted with a reasonable selectivity. It would be very interesting when you go into this type in general of MOFs to have in the metal the linkers that they would resemble to one organometallic. That is what did Dinka. That is a work that I like very much and I always refer to, in where Dinka used the nickel and used now the ligands as a linkers that they could modify the nickel to be able to carry on ethylene dimerization into butene. And as you see, it was successful, obtaining very high turnover frequencies and very high turnover numbers. Sites in the nodes, you can put sites on the ligands. What about inside? Besides nanoparticles that have been introduced, we thought about the possibility to introduce very well defined metal clusters in this case. Well, in collaboration with Emilio Pardo from the University of Valencia, we prepared in 3 steps here a MOF by doing a transmethylation and then doing an exchange and one reduction to obtain finally, as you see, clusters of palladium, clusters of 4 atoms, very well-defined clusters of palladium. Those clusters, they are at the wall, as you see. This will be the view along the channel, okay? And that will be another view. Very well-defined. And reasonably stable at the temperatures that the MOF was stable. And it was active. We tried this for a carbene-mediated reaction at the azoacetate here, and the results we obtained on yields and selectivity were at least at the state of the art for this type of reactions. So we could make well-defined 4 atoms clusters of palladium. We could make then 2 atoms clusters of palladium. They were also active, and we could make even single atom. In this case of platinum, you see that we have single platinum atoms that they are coordinated to 2 carboxylates and the rest to the molecules of water. Molecules of water that they will be able to react with CO and to produce hydrogen in a water gas shift reaction. And what was curious to us, it was interesting, is to see that that reaction could work even at very low temperature. Of course, when you work with inorganic catalysts, you work at higher temperature. If we use Arrhenius plots and simulate or extrapolate what we would obtain at higher temperature, the turnover frequencies that we obtain with this catalyst is not too different to the ones that you would obtain with platinum on some solid catalysts. With what I have said up to now, we have first part that we said in the enzymes, well-defined, single or multiple sites, but we have said nothing now, up to now, about the cavities of the reaction occurs and how we can influence those transition states. So you have in many enzymes in where that pocket, for instance, is quite hydrophobic. So that allows the reactions to take place with organics even in water media. Can we change with these materials the surroundings of the active sites that we have in the MOF? Well, look at in this MOF. This MOF, you have a carboxylate here, then you have a chain, a hydrocarbon chain, another carboxylate, and with the 2 carboxylates and the organic chain, you bind these 2. So what we can do is, in this case, instead of using 2 carboxylates, use just one, and then to keep the alkyl chain here. If we use this, this will coordinate, of course, with the metal, but will not coordinate here with the other series of metals. And then what we'll be obtaining is a type of ribbon here with the alkyl chains. Those alkyl chains can now go self-assembling, and by going self-assembling, we can have now a layered product, a 2D MOF, and we obtain a 2D MOF, or even they can go and make mesoscopic, in this case, mesoscopic single layers of MOFs that they are well structured. If you believe me that by characterization we demonstrate that we were obtaining either layered MOFs or this one, look at what type of material we have now. We have now a material with large surface area in where we have the metal here, and we can generate Lewis acidity by creating, for instance, defects into those. But we are going to have a very hydrophobic environment inside. That means that by having this hydrophobic environment inside, we can work in water media without destroying our Lewis type of catalyst. Well, we should be able now to have Lewisides, hydrophobic media, and to carry on reactions in water media. And that is the case for this three-component condensation. This is the mesoscopically organized material that I showed you before, highly hydrophobic. This will be the regular MOF that was used for starting. As you can see here, the difference in initial reaction, but also on the stability for longer time, it's much higher for the material we did. So we have now, say, cavity, highly hydrophobic, in where we can have active sites, but we have also a hydrophobic that we can use it just as a reactor, even without active sites. That means we can have active sites outside, but the reaction will occur inside. And this is what happens. We took a reaction from the literature, which is a Michael, in where organocatalysts are used for getting the final chiral product. So this is the reported in the literature organocatalyst to carry on the enantioselective Michael reaction. And it is true. When you do that in the media, you obtain 99% enantioselectivity with 14% yield. Water present in the reaction. Now, if we use that highly hydrophobic material that we made as a reactor, the reaction will occur inside with this one and the reactants in the presence of water, because water will be remaining outside of the cavity. And what you see is that with this material, not only we keep the enantioselectivity, but we have a much higher activity. If you use the MOF instead of the material that we have produced, you get the same enantioselectivity, which is due to the organocatalyst that you add into the reaction, but the conversion is much lower. It's the same that you had before. And this applies not only for one reaction, for several reactions, not only with water with another solvent, but with different solvents, and you see here, always keeping the enantioselectivity and always increasing the final yield of the product. We should not forget that we have hybrid materials that in catalysis, either the catalyst we have gives a very high turnover number, or if not, we have to regenerate it, and we have to use it multiple times. That means that a factor very important in catalysis is stability. The catalyst has to be robust. So, for applications that they require more demanding conditions, then we have to use inorganic catalyst. But we want to keep what we were learning from there. That means well-defined, single isolated sites, and also how to change the environment in where the reaction will take place. So let's move now into purely solid inorganic ones. And here we have a silicate, more specifically a zeolite, in where we have short range and long range order, and we have a mesoporous material, for instance, with long range order. But let's concentrate on the zeolite here. Here in the framework, we can do now isomorphic substitution. We have substitute silicon with other metals. If we use a trivalent metal, we'll generate acid sites. But we could also substitute with some transition metals. We can substitute with titanium, for instance. And then, here in the structure, we'll have well-defined single isolated sites in where we'll be able to modify the adsorption properties by changing the composition around the diffusion, and also, as I will show you later, we'll approximate one step into the behavior of the zeolites by stabilizing through weak interactions, like in the zeolites, in the enzymes, by stabilizing with weak interactions the transition state of the reactions. Well, metals, titanium, well-defined titanium, tetrahedrali coordinated. Any technology achieved to do that in tetrahedral positions in ZSM5. That was a medium pore zeolite, 5.5 Armstrongs, and then the purpose was to be able to expand that into larger pore zeolites in where we could process larger molecules. One candidate was titanium beta that was able to be synthesized in that time with silicon to aluminum ratio of 20. However, what we learned from titanium silicalide is that to get successful synthesis, we had, or successful catalyst also, we had to have pure silica materials and then introduce the titanium, and we have to do it in absence of alkalines. So to be able to make the titanium beta, first we have to achieve to make the synthesis of pure silica beta, and this was not obvious in that time at all. Secondly, we had to do it in absence of alkalines. That was not obvious at all in that time. But finally, we obtained the titanium beta, and we expanded to other materials like titanium MCM41 and mesoporous materials in general, and into 2D zeolites, the delaminated zeolites, we could also introduce accessible titanium to the reactants. Well, the characteristics of those materials is that they gave excellent activity and selectivity working with organic peroxides. And you may say that what was the advantage? Why we want to use organic peroxide when titanium silicalide was able to work with hydrogen peroxide? Well, I will tell you. One is selectivity. And the second, remember what we said about the surroundings of the active site. With this type of molecule, of structures, by secondary synthesis, we could introduce other groups around. So we could modify what was the surrounding of the titanium atoms. Then what we saw is that these materials, they were extremely selective for carrying out the epoxidation of olefins using terbutyl hydroperoxide or using cumin hydroperoxide. Then you can go into a system in the same process in where what you do is you generate there in the process the peroxide. You start with cumin, then you oxidize into cumin hydroperoxide, you transfer the oxygen into the propylene to make the epoxide, then with the alcohol that you have, you go now dehydrate, hydrogenate, everything inside of the same process, not the same reactor, but the same process. And then you go and regenerate again the peroxide. So by following this route, at the end, what you do is the olefin plus hydrogen plus oxygen to the epoxide. The cumin is just the transporter that you have there. Well, that is what is called now the cumin, the Sumitomo process. We license the catalyst and all that is Sumitomo, and together with them, we develop the process, and we have kept working with them very successfully and very happily, and we are now already in the third generation of catalyst for this process. This titanium but you could introduce also other metals and to do other reactions, other chemical reactions that when you look into the literature, you see that that was all chemistry and could be made better. This is just the first plant that was installed in the Sumitomo with about 30 tons of catalyst in the plant. I was saying, look at the reaction for making lactones. You start from cyclohexanone to make epsilon caprolactone, and how it is made is using peracids. But peracids are explosive, are not the most friendly products. The question is if we could make it by hydrogen peroxide, with hydrogen peroxide. But hydrogen peroxide is not nucleophilic enough to attack here to this carbon. So then, what we had to do is to make that reaction more prone to be carried on. So in the way we thought was not to activate the hydrogen peroxide, that will lead into less selective process, but to activate the carbonyl. And we could activate the carbonyl by introducing a Lewis acid site. A Lewis acid site in the framework of the zeolite, and what we wanted was a Lewis acid site able to polarize this bond, to increase the density of charge here, but at the same time, we didn't want that it will form peroxides, because then it could oxidize other groups if we have those groups there. So now, we saw the one with these conditions was tin, and we introduced tin in the beta zeolite. We could achieve that finally. Tin will polarize that, and we saw by in situ infrared, we saw that polarization. And then working with oxygen 18, we saw that indeed in the mechanism it went through a Kriege type of adduct, and we preserve in the molecule the oxygen of the carbonyl, and the oxygen from the hydrogen peroxide is the one that was introduced into the ring. This catalyst, because we were activating specifically this group, was not only active, but it was selective, very chemoselective. Take here one molecule in where we have the carbonyl, and we want to make the lactone. We don't want to oxidize the double bond and to make epoxides. If you use metachloroperbenzoic acid, which can be a typical, say, method to obtain the lactones, you will see that you obtain some of the lactone, but you will obtain mainly products in where the double bond has been also oxidized into the epoxide. On the other hand, if you use titanium zeolites, titanium is also a Lewisite. It may also polarize. You use titanium zeolite, since titanium forms the peroxides, what you obtain are fundamentally the epoxide. With tin, we were obtaining 100% selectivity to the caprolactone, to the lactone, excuse me. Okay, so now what we would like to know is if the real active site was the tetrahedrally coordinated tin, as you put here, or how we had to have that tin for carrying on the reaction. Well, what we did is then use tetra-coordinated tin to carry on the reaction, to do, better said, to do molecular modeling, theoretical calculations, and we saw that the reaction was not working. However, when you hydrolyze one of the tin-oxygen silica bond, and you generate now one tin OH, now yes, the reaction proceeds very well. The tin, as we saw, polarizes the carbonyl. The OH bonded to the tin activates the hydrogen peroxide that attacks into the carbon now and gives you the final product. So what we want now is not to have sites tetrahedrally coordinated, but tri-coordinated in that one. And we have to find a way to produce those sites. Well, we found one way of doing that. We use a molecule, a pro-molecule, which is a deuterated acetonitrile, in where we could differentiate when interacting, in this case, with the molecule, which things they were coordinated with 4 oxygens, what things were coordinated with 3 oxygens and the silicon, and 1 OH. And you see a very direct correlation, excellent correlation, between the amount of hydrolyzed tetrahedral, so 3 here and 1 OH, and the initial rate of the reaction. So we know the sites. And that was not only for the Baeyer-Villiger, but for the other reactions that we were carrying out, like hydrogen transfer, for instance, Merwin-Pondorf type of reaction. Again, this is the site. Here is how we activate that molecule to be able to transfer the hydrogen. So we know the type of sites, we know how to generate them, so we can produce active catalyst. This would be very interesting because it can work in water media. It's a highly hydrophobic material. By being a highly hydrophobic, can work in the presence of water, and therefore we can use it for biomass. And we use it here for a diastereoselective water-resistant heterogeneous Lewis acid. For carbon-carbon bond formation, was working very well. And then others, fortunately, have expanded into other reactions with biomass, either working with glucose or working with derivatives from the lignin or derivatives for lactic acid, etc. So you see that in these materials we can obtain well-defined single isolated sites. But what about the other factor that we wanted with enzymes? In the enzymes, remember, they had groups here that by weak interactions, they are able to stabilize that transition state. But in the zeolite, we have also cavities. And in those cavities, when the size of the cavities approach to the size of the molecule, or to size to the transition state, you are going to have also interactions with the walls. So you are going to have weak interactions, van der Waals interactions, hydrogen bonding, dispersion forces. So if the shape is the adequate, that those interactions are the adequate, we can have something along the line of what you will have in one enzyme. Let me show you that that indeed happens. Many acid catalytic reactions, you go through carbocations, take one carbocation here, the corresponding carbocation of the estyrene. Here you have one large pore zeolite, mordenite, with sites in two different points of the channel. So then we have now another zeolite, ZSM5, in where we have two different spaces. One in where the channels they cross with larger void, and another in the channel with smaller voids. So when closer will become the size of the molecule to the size of the cavity, better will be this type of weak interactions that I am saying. We made calculations first saying no interactions with the wall, just interaction with the framework on the acid site. And you get the stabilizations that you get from these carbocations. You stabilize in all of them. When now you start to consider, by calculating the dispersion forces, you start to calculate now the interactions with the walls, look at the big jump in stabilization. You stabilize those much more. And when you come now into the zeolite ZSM5, in where you have the crossing points and in where you have the channels with different void space, you see that the stabilization is different. Stabilization is larger when you go into the channel instead of the void space. So what that is saying, that now, if that is the case, that should have one impact in our reaction, in our rate of reaction, in our selectivity. Reaction may take place preferentially in one channel versus another, in a cavity versus a channel. And therefore, you would like, when you make the synthesis, to locate the sites in one cavity and not in the other, in one channel and not in the other. So I will show you how that happens in the case of reactions. The group of Enrique Iglesias did a beautiful study on the carbonylation of methanol to obtain acetic acid. They used mordenite as a catalyst, and mordenite has the 12-ring pores and then have 8-ring pores connecting the 12-ring pores. By working with kinetics and spectroscopics, Enrique and his team, they saw that fundamentally for me the decarbonylation was occurring in the A-member rings, and the hydrocarbon formation, which is the competing reaction, the reaction that you don't want, that was occurring in the large channels. Moreover, they conclude that in mordenite, the methoxy groups in the 8-member ring are more reactive than in 12-member ring. That is a hell of a lot of information. And then we went mechanistically to see if that was indeed the case and how we can manage it. So here we form the methoxy in the 12-ring and in the 8-ring. And then we went through theoretical calculations and calculate the reaction of that methoxy groups either with CO, carbonylation, that is the reaction we want, with water that we'll have present, you will hydrolyze the methoxy, will give you back the methanol, or the methoxy that you have formed that can go into dimethyl ether, and the dimethyl ether can go into hydrocarbons, things that we don't want. Take the site in the 12-member ring, the methoxy in the 12-member ring. Calculate the activation energy. And what you see is the most favored reaction, that with the lowest activation energy, is the formation of dimethyl ether and hydrocarbons. Just what Iglesias was saying in his work. The less favorable here will be the wanted reaction, the desired, which was the carbonylation. What happens when you go into the methoxy in the A-member ring? The less favorable is the formation of hydrocarbons, correct. However, in the type of calculations that were done there, in where we were not considering at all the interactions with the wall, just the acid and the methanol, and the methoxy and the other molecule, the CO reacting, without considering any stabilization from the wall, what we saw is that the carbonylation was not the most stable one. What didn't give the lowest activation energy. So, if one would look only to the zeolite without considering the interactions with the wall, it will be losing the potentiality to explain the results. So what we did then was to introduce the interactions with the wall. And when we introduce those weak interactions with the wall, that means van der Waals, hydrogen bonding, dispersion forces in general, what you see is that nothing changes in the 12-member ring. The less one is the formation of hydrocarbons. But when you come into the 8-member rings, now the most favorable, the one with the lowest activation energy, is indeed the formation of the acetic acid decarbonylation, in agreement with the experimental results. Why is this? This is because in the case of the 8-member rings, the methoxy takes a very unusual orientation in relation to the 8-ring channels. Normally the molecule will absorb here, will absorb in this way, and now methoxy is absorbing in that way. This gives maximum stabilization by dispersion, by weak interactions in the 8-member ring channel for the carbonylation. So you see here how important are those weak interactions for carrying on reactions inside of the zeolites. So then you have to have the right cavity for doing that, too large no good, too small neither, the right one, and therefore when you have several of them, you want to have the active sites there. So another important point to control in your catalyst is to be able, by direct synthesis, if possible, to locate the sites in one channel or in another channel, in one cavity or in another cavity, in where the reaction is going to take place. This is what Joaquín Pérez Pariente tried to do, and his team, they try to do, by locating selectively the acid sites into the 10 ring or into the 8 ring in the case of ferrierite. Or what will happen in the case of ZSM5 that we were more interested. In the ZSM5, you can locate the aluminiums that will produce the OHs pointing into the crossing of the channels in where you have larger volumes, or into the channels in where there will be a smaller one. So depending the type of compound that you want to form, you would like to have the aluminiums there, you would like to have the aluminiums here. How to do it? One way will be, like before, to use different templates and alkalines, playing with that. The other is how we did, that is introducing different trivalent elements, boron and aluminium. Boron preferentially would go into those in giving at the crossing channels, while the aluminium in the presence of boron, it will go into the channels. If this is that, we should be able to control now selectivity in our catalyst. And this is what happens. We took a commercial catalyst in this case and make with our method another catalyst. We synthesize a catalyst with the same silicon to aluminum ratio, the same crystallite size, but putting selectively into the channels smaller places, putting that into the channel, the aluminiums, and therefore the protons. We crack hexene, we obtain propylene, but propylene can keep reacting and then going into aromatics and alkanes. If we could avoid that reaction, they will require larger spaces, we should increase the selectivity into propylene. So by having the sites into the channel preferentially, we should improve it, and that is what we observe. We increase the amount of propylene, and we decrease the amount of the products made by molecular reactions requiring higher volumes for reaction. Well, we can apply those concepts into commercial processes. We can go from methanol to propylene. When you go from methanol to propylene, you make propylene, but then propylene keeps reacting, as you saw before, making now larger products like aromatics and alkanes by transferring hydrogen. What we would like in this case is to have the active sites not at the crossing, but in the channels. Then we should decrease the conversion of olefins into the aromatics. That is what we did. By working on the synthesis along this direction, plus by post-synthesis treatments, we could achieve a catalyst that was more selective and with a longer catalyst life, because the larger molecules were not blocking as much as in the regular catalyst. And 150 tons of that catalyst have already been produced. So you saw that if we want to approach into the enzyme with everything that I said, we want to have well-defined sites and to put them in the place where we want in our structure. And we want to have the cavities. And we want to have the weak interactions with the transition state in that cavity. So we have to have the right size and shape of that cavity for doing that. And we want to have there the active sites. So this is the challenge now. How we face that challenge? To face that challenge, we thought on molecular imprinting. what do you do with molecular imprinting? With molecular imprinting, you take a mimic of a transition state, and then you go and you imprint in a polymer or in silica, for instance. Then you remove it, and you leave what could be the pocket of the cavity in where the transition state will fit perfectly. On top of that, you will have to put the active sites here. And that has been attempted for polymers, has been done also by silica. The problem it becomes when you go and you calcine to remove what will be the mimic of the transition state. Then it's difficult to keep exactly that shape. And it's not easy neither to put the active sites exactly in that place. However, using this concept, we can go into another type of materials. How you make zeolites? You make zeolites, in this case, by using organic structure directing agents. What is the purpose of the organic structure directing agent? To maximize the interactions with the walls of the zeolite that you are forming. That means to minimize the energy of the hybrid material that you form here in organic. So that means that organic structure directing agent is maximizing already the interactions with the walls. But all that is what we were saying before in the zeolite that will be convenient for us. Furthermore, the compensation charge that you have for the organic structure directing agent is located exactly here in the cavity where the structure directing agent it goes. So that means that we can try to use now as organic structure directing agents mimics of the transition state of the reactions that we want to catalyze. This is what we did. We look into different reactions, 2 from petrochemistry, 1 from chemicals. And we look into the potential transition states. And then what we made were mimics, as you saw, of those potential transition states. And then we obtain zeolites, different ones. ITQ-27, not very usual, with 12 and 12 rings. We obtain ITQ-64, neither very usual with 12 and 10 rings, and MIT-1. And when we use them as a catalyst, with the same crystallite size, of course, what we obtain is that the turnover frequency of the materials that we synthesize was more than twice the turnover frequency of the commercial catalyst that has been optimized already by many years. Same for any of the 3 reactions. Furthermore, when selectivity is an issue, like isomerization of ethyl benzene into silenes, you can get para, ortho, meta silene. The para plus ortho that are the ones that you would prefer versus the meta, that selectivity is much higher in the case of the mimic of the transition state that you use. Okay, you may say, well, this is fine, but of course you are mixing there a transition state and mimic of the transition state and the cavity and also the active size that you need. So what we can do now is to use just one reaction in where active sites are not needed. The only thing that is needed is the cavity. And if you have the proper cavity, that is going already to give you the final product. And these are Diels-Alder reaction. So what we did is we took a Diels-Alder reaction. This is the product. As you know, in Diels-Alder reaction, the final product is very similar to the transition state. So then we can use the final product to make a mimic for the transition state. This is the mimic that we find. And we obtain, in this case, one polymorph of beta zeolite, polymorph C. Pure silica, so no active sites. Then we compare its activity with the other 2 polymorphs of the zeolite. Polymorph C we obtain, and then we have in beta zeolite the polymorphs A and B. So let's see we can distinguish not between different zeolites in that sense, but between different even polymorphs of the zeolite. And what we observe here is that, excuse me, the activity when we use the polymorph C, the Beck, was sensibly higher than when we use the polymorph A and B, which is the beta zeolite. But if you look into the kinetic parameters, you will see here that the enthalpy of activation is lower for the polymorph C than it is for the beta zeolite. And the entropy, the loss of entropy of activation is higher in the case of the polymorph C, the Beck zeolite, than in the case of the beta zeolite, because the fitting is better in that case. Okay, so we have seen how we can in some way approximate into the weak interactions that you have in the case of the enzymes and the weak interactions we can get in our inorganic solids to try to stabilize that transition state. Let's go into the final part of my talk in where we'll generate now single atoms, single metal atoms, transition metal atoms, platinum, palladium, gold, nickel, cobalt, etc. Already a long time ago, Bruce Gage was working heavily on that, and he was obtaining single atoms inside of the cavities of the zeolite. In his case, he was obtaining rhodium, iridium, different ones, making them as carbonyl complexes. That was okay. The problem is, of course, that if you have to work at high temperatures or at higher temperatures, they will decompose and then the metal agglomerates. In the case of Christophe Copperet and Jean-Marie Basset, also they obtain beautifully single isolated metal atoms that they can work at low temperature, they can work very well, but when you will go into higher temperature, then they will decompose and they will go into agglomeration. Our colleagues have been trying hard to make those single atoms on solids and that they remain stable, and in fact, Maria Frizzani Stephanopoulos show that it was possible to obtain a large proportion of single atoms, also obtained clusters and nanoparticles, but a large proportion of single atoms, platinum and gold, on different supports. And the activation energy that was getting was exactly the same for all of them. So single atoms could activate, in this case, for a water gas shift reaction, platinum and gold as single atoms. Others have obtained it with other supports, like carbon, for instance, or carbon with nitrogen, and the purpose of the nitrogen is to better retain, better interact with the metal and avoid that metal sintering. So if you want to obtain single isolated metal atoms on, say, carbons or into oxide supports, the interaction with the support has to be quite strong. Otherwise, they will migrate and will agglomerate. But I believe that one should take into account another thing. It should take into account, this is another single atom, the hatching obtained by supporting gold on carbon, and then removing the clusters and the nanoparticles with treatment with aqua regia and leaving only single atoms, and they were active for hydrochlorination. As I said, the interaction with the support has to be strong to avoid agglomeration. But we have to think that when we carry on the reaction, by the catalysis principle, our reactants, they have to interact, and sometimes quite strong, with our active site, in this case the single metal, and then can facilitate, in some cases, that migration on the surface of the catalyst. So what we did was, in collaboration with the lab from Blue Haven National Laboratory, to look at into the microscopy how those single atoms, they evolve during the reactions, either during treatments with oxygen and hydrogen, or during oxidation of CO, or water gas shift, or reduction of nitrogen oxide. And what we saw is that in many of those cases, the single atoms, they were migrating. They were migrating and they were getting agglomerated into clusters, and sometimes even further into nanoparticles. And in a parallel work on the reactor, we saw that in some cases, what were active were not the single atoms, but were the clusters that you were forming during the reaction. So one has to be sure that during his reaction, the same sites that you have when starting are the ones that they are going to be active after that, and not others that you will form during the reaction. Some time before, to show you with one practical case, we were supporting single atoms, gold atoms, on carbon nanotubes, and we were performing the oxidation of thiol to disulfide. We were obtaining extremely high two-number frequencies. But then, when we look carefully what was happening with the catalyst, what we saw is that during the reaction, those single atoms were forming clusters. And what were active really is the clusters. That means that when we make the clusters, right away, they were giving us the desired activity that we wanted on the catalyst. Clusters have shown to be active in other cases, and here copper and ruthenium clusters, they have been used for hydrogenation in a number of reactions. We want to keep, in many cases, clusters stable under any atmosphere, and we want to have very small nanoparticles stable in any atmosphere. That means under oxidation, under reduction conditions, we want to keep them even at very high temperature. So what the people did was to synthesize one-pot nanoparticles when you make a zeolite. The idea was that those nanoparticles will be formed inside of the cavities of the zeolite, and then they will remain stable because you will decrease the diffusion rate of those metal particles, and therefore you will avoid or diminish the rate for formation of larger particles. And this was done by mobile, showing that indeed they were obtaining small particles, or by two groups, as you can see, the group from Iglesia in Berkeley. They could obtain particles around 1.3. The group of Professor Yu show also the same exactly with palladium, obtaining particles with 1.5. We wanted single atoms. How we can make single atoms in our zeolite? We took chabazite. We started here with nanoparticles, and we made the material, and we obtained the nanoparticle in the zeolite, but when we calcine in oxygen at 600 degrees, what we saw in the zeolite were single atoms. We had single atoms of platinum. We see it by microscopy, and we see it also by EXAFs. Then when we go and we reduce, they start to agglomerate, and they form clusters, and finally nanoparticles, the same that our colleagues saw before, around 1.5 nanometers. What is interesting is that if now we calcine again in the presence of oxygen at high temperature, we break down those small nanoparticles and we make again single atoms, and can go during different cycles. Nevertheless, we wanted to obtain small nanoclusters, subnanometric nanoclusters, and in different reaction conditions, even reducing in hydrogen at temperatures of 600. So we decided then to go into another direction. What we did in this case is starting with a precursor of ITQ-1, pure silica precursor, and in the precursor we swallow that layered precursor with surfactants in where we had the precursors, metal precursors of could be the single atoms of the clusters. Then we close those with temperature, and what we obtained were single atoms and clusters engaged in the cavities communicated by 10 rings one with another. This is exactly what we obtained. But the interesting thing is that we have this even at temperatures as high of 650 degrees in hydrogen. So they are extremely stable nanoparticles. Did with platinum, but we could do it with gold also, and we can get the gold nanoclusters. And as we predicted long time before, if we have gold nanoclusters, then we can use that to initiate radical oxidations in the case of, for instance, cyclohexane oxidation. And this is what we saw with the clusters of the gold. We can put other metals and achieve the same thing, like iridium. In this case, we can have single atoms, and we treat with hydrogen, we get clusters, subnanometric clusters, as you can see there, even treating at different temperatures in hydrogen. We could look into where those nanoparticles are located, and I will show you that when working with ZSM5, pure silica. Platinum in pure silica ZSM5. When we make the synthesis, we obtain single atoms. And then by working with HADF and integrated differential phase, we could see the platinum atoms, the structure of the zeolite, and then superimposing the two of them, we could see where those platinums were located. And what we see is that the single atoms of platinum, they were located regioselectively in the sinusoidal 10-member ring channels. When you calcine, you have still single atoms, and they are located in the same places. So that means that we have points in our 10-member rings that they are able to stabilize very strongly the single atoms that we have there. Well, if you reduce now at high temperature, 600 degrees in hydrogen, now you make clusters of about 0.5, 0.6 nanometers, and those clusters are still located into the sinusoidal 10-member ring channels of the ZSM5. You can make it with platinum and potassium. You can make bimetallic with platinum tin in the presence or not of potassium, and then you could obtain catalysts in this way that they are extremely stable in oxygen and in hydrogen atmospheres, so they could be used very well for dehydrogenation of paraffins, propane into propylene. The life of those catalysts is quite long because they do not agglomerate very easy, and furthermore, they can resist very well the redox cycles, oxidation and reduction. One example to show that everything I have been saying about small clusters, subnanometric clusters of very small nanoparticles, we could find direct applications. Here is one example for the production of chemicals in where this is the product to be obtained, and how was done that in industry was through a Merwin-Pondorf type of reaction in where you use acetone and you use aluminium isopropoxide as a catalyst. Of course, such a process, it produces a lot of waste. And furthermore, the mass efficiency is small because part of the reactor is occupied by the acetone here. But if you look, the amount of waste that you form is quite high. However, in our case, with a bimetallic catalyst, with very small nanoparticles that we have there, very stable ones also, we could carry on the oxidation selectively, and 98% yields were obtained, practically without any waste. And the production today is further than 800 tons per year using our catalyst. I have come to the end of my lecture, and here I have many people to thank, many. I will say first that I want to thank all of you. That means all my colleagues. I have been learning from you and from our past colleagues. And we are passing what we are learning to the next one. That is in the way we'll progress. So thank you all to all. I want also to thank, not specifically to any one of the people that they have participated, of course, that is normal, but I would like to thank to all the ITQ, all the people in the ITQ, all the ones who believe in the idea and they push to this for being a reality today. Finally, I would like also to thank to Professor Heinemann, because he was an initiator of the catalysis in Spain, and myself, I am the third generation of those that he took into the United States for doing the postdoc, and then came back to Spain and transmit to us what they were learning there. Thanks also again to the organizers. Thanks, Enrique. As I said, I know the frustration all of you have, and it's the same frustration that we have by not being together and celebrate together the Heinemann lecture. Thank you.